Hi, everyone, and welcome to Backer Breaks It Down. In this episode, we continue to look at proportionality theorems. Specifically, we will look at the proportional segments theorem. Okay, so look at this diagram. Looks a bit complex, doesn't it? And intimidating. But really, you've seen something similar to this. So I'm just going to go back in time here. Remember this one? Okay. So if I were to say chop off the top part of this triangle, okay, that's how you're getting the diagram in today's lesson. It's basically the triangle proportionality theorem, but the two sides never meet and join each other, creating that triangle shape. Okay. So it's essentially our triangle proportionality theorem, but since we've chopped off part of our triangle, we just have these parallel lines creating segments, that's what we're going to be working with, right? And so you're going to see a lot of similarities between this theorem and how we set up the proportions and what we did in the previous episode. Okay. So the proportional segments theorem says if three parallel lines intersect two transversals, then they divide the transversals proportionally. Okay. So our three parallel lines are R, S, and T. Okay. And our two transversals are the other two lines clearly, right? L and M. Okay. And it says they divide the transversals proportionally. So let's take a look at those transversals. Let me get a different color here. Okay. So taking a look at L, it's been split. Those three parallel lines created these two segments. One of them is UW, the other one is WY. And so notice that UW and WY create one of your two ratios. Okay. And then the other segment, so VZ has been split into two. So you have VX and you have XD, and that's where you're getting the other ratio from. So it's really, really similar to what I was just talking about with the triangle proportionality theorem. So we're looking at the two sides and we're creating ratios. So I can do the whole top over bottom equals top over bottom. I can do part over whole equals part over whole. Honestly, it's when I see the diagram, I'll know the best way of setting it up. Okay. So I know you're show me, or you're not, whatever. Okay. So here we wanted to find X. X is representing the distance between Royal Avenue and LA Avenue. So it's right here. Okay. And so they wrote this proportion here. They have X over 1.2. Okay. See it? Is equal to 2 over 1.6. See it? Yeah, so they did top over bottom equals top over bottom, and that was their proportion. Cross multiply, you get X is equal to 1.5. Okay. So let's do this. So number 5, what jumps out at me right away? The 18 is representing the whole left side. That was weird. So I should be oh, what is the whole right side? So 8 plus 4 is 12. Okay. And then they want me to find this question mark here, and that's the lower part. So I should do part over whole. So I could be question mark over 18, part over whole equals, well, I'll use the corresponding part. So the 4 over 12, part over whole. And then I can simply cross multiply to solve. And so I get that the question mark is 6. Okay, easy. When I look at number 6, the proportion that's kind of jumping out at me is to do top over bottom. So here with the 5 and the 3, top over bottom. So 5 over 3 equals, then make sure you write the other ratio in the same order. Pay attention to those corresponding parts. So the top part would be 2x minus 8, and the bottom part would be 6. And there's my proportion. Top over bottom equals top over bottom. And so I end up with x is 9. Okay. But you can see definitely in number 5, like these two, if they just went a little further, they would make that triangle. So the proportional segments theorem is just a corollary of the triangle proportionality theorem, because I just chopped off the top part of the triangle to create these diagrams. And so I am getting a similar proportional relationships, hence why this summary calls it the corollary to the triangle proportionality theorem. So if 3 or more parallel lines intersect 2 transversals, then they divide the transversals proportionally. That is how Becker breaks it down.